Our next presenter is Marcelle Bonterre. He's Senior Machine Learning Engineer at Turnitin, which is a program I've used many times myself in the education space. And the term he uses to describe himself is he's an artist. Welcome, Marcelle.
Thank you, Beverly. I need to be able to see the slides. So as Beverly mentioned, my name is Marcelle, and I worked at Turnitin. The most recent project that I work on at Turnitin is, as my friend joked, the discriminator side of a GAN. We call it the AI writing detector at Turnitin. And essentially, we would like to, for our customers, say whether or not any text that comes through our system was written by a human or a machine, which is itself, it sounds like an impossible problem because the machines are getting bigger and bigger, and the convergence between the way the humans speak and the way the machines speak is going in the wrong direction. So one of the most pressing matters in our design of that system was the performance of it. And essentially, at every step of the process, we needed to optimize the performance, both for cost and for meeting our customers' expectations for time. And the graphic that I have in front of you is essentially, this is specifically from TorchScript by PyTorch, is essentially what a pipeline could look like for a machine learning project of this size, where essentially you have to serve a model to any number of clients with a large throughput. And at any point in this pipeline, you could choose to spend infinite resources optimizing. This talk in particular will focus on the second phase in the pipeline after the model has been trained and is being prepared to go into production somehow and being served somehow. So the question of should you even optimize always comes up. It's expensive, it's tedious, it's possibly an infinite loop if you just are continually searching for wins on speed or space or memory consumption or any of those things. And it is not to be taken lightly whether or not you should or should not optimize. And so these are some reasons why you might. In the past, it has been a lot easier to choose not to and to kind of punt the decision of whether or not to optimize down the line because it was difficult and complicated, possibly required expertise that wasn't available on your team. And today I would like to say that that is less true. One easy and, in my opinion, the best idea, if you can do it, is to use a smaller model. And in most cases, for most organizations, that is likely the truest and easiest solution. In the age that we're in now, it's very natural for organizations to be excited by ChatGPT and all of the other big LLMs that are being cloud hosted, and very quickly the cold water dashes on them when they discover the price of the inference, the quantity of their traffic going through those servers, and then, of course, the legal department hates that you're shipping off your data elsewhere. So if you can't afford to send your data to another company so that they can improve their LLM, and you need to have the model in-house, what do? So these are a list of techniques that you can employ that are now a lot easier to employ than previously. And the last one, the vendor-supported one, is sort of the escape hatch for we don't want to do this in-house or as much in-house. What else do we have out there? So the first technique is called pruning, and it essentially is a productionization of the lucky ticket hypothesis. The lucky ticket hypothesis is essentially the idea that for any neural network, there exists a smaller neural network with fewer parameters that does the same thing at the same level of quality and is therefore cheaper because you're not using the rest of the neurons in that network. The productionization of it via pruning is a mechanism to allow you to find that smaller neural network by disabling via a number of strategies other neurons in the existing network. So I've listed a few strategies here. These are some strategies that PyTorch exposes, and there are other strategies that other tools expose, and they all come down to the same thing, which is which of these neurons should we switch off? Switch off being zero them out so that they don't compute, or they're not used in the computation. The next technique is quantization. And quantization, like pruning, works at the neuron level and essentially seeks to make the network smaller by changing the memory requirements of the pieces of the network. The pieces of the network, in this case, being the floating point weights. And if you change from using floating point numbers to integers, they cost less, as is evidenced by this extremely easy to observe graphic. PyTorch exposes two different kinds of quantization options, dynamic and static. And essentially, the difference boils down to when and where is the quantization happening. For the dynamic quantization, at runtime, it will determine the quantization of the activations, and at the end of train time, or some offline time, it can quantize the weights and give you a new model with quantized weights that are statically quantized. The static quantization is everything I just described, except there's no computation or determination that needs to happen at runtime for the activations. It's all done upfront. An example of this is the difference between the static and the dynamic quantization. For the static quantization, all the code you need is just that little blob at the top. A lot easier than it used to be. And for dynamic quantization, here we have an example where this particular model is having quantization only apply to its linear layers, and the particular kind of integer that it's being quantized down to is listed in the D-type parameter. And then we can also see that the quantization has a particular effect on primarily the speed, but a little bit also the quality of the model. We can see that the F1 score is nearly the same, but dramatically the speed is different, but that is not necessarily true in all cases. Another option that we have available to us is TorchScript and its whole family. TorchScript, like a few of the other options that we have coming up, is one mechanism to escape Python and its limitations. Essentially, TorchScript is a restricted subset of Python that has been optimized, and it is a system built into PyTorch that allows you to convert your model from using normal Python data structures to using the optimized TorchScript data structures. And you can choose then to go one step further and go all the way to data structures that are portable across language runtimes. One difficult, or not difficult, but one kind of forced choice that you have to make, or that your situation might force you to make, is whether or not to trace or script. where scripting is just lowering the Python to that TorchScript level, and tracing is lowering everything from the model down to a serializable level that can be serialized across runtimes that is independent of Python. The speed up that you get from choosing to script or to trace can sometimes be quite dramatically different if you choose to trace. Tracing is often a lot faster than scripting, and the primary constraint that allows you to determine which one you need is the limitation that I listed at the bottom, that with tracing, you don't have the opportunity to do any sort of branching logic. So what I mean by that is, during the process of tracing, you run the tracing system across all of your model and and you push some data and information through your model to force it to make an inference. Everything that the model touches is what gets traced and captured into the system for serialization. Anything that doesn't get used, for instance, you have conditionals within your model for whatever reason, then those subsets of the model that were hidden behind conditionals will not get traced at all. One other option is PyTorch's FX system, and it is, in this situation here, I've listed it as a Python to Python transformation pipeline, and it essentially takes you from the Python you wrote to Python you didn't write via an intermediate representation that they have developed. Similar situation, you can trace your model with the tracing facilities, the tracing functions that they exposed in the library, and you end up with an artifact that you can then use for inference. And then finally, we have module fusion, which is the process of taking a multitude of operations and pushing them into one operation that is optimized outside of Python. So all of these things are essentially packaged versions of everything I just described. So TorchPrep is a way to do all of the scripting and pruning and quantization and a multitude of other things, all automated for you, built by PyTorch. It is experimental at the moment, and the purpose of TorchPrep is in service of using PyTorch TorchServe, which I showed earlier. And it is essentially in service of doing that second step automatically before you then configure TorchServe for the various pieces of the parameters that you see here in the third stage. AWS Neuron and Intel Neuro Compressor both do very similar things, which is for the particular compute that you'll be running your inference on, you're running your model on, do hardware-specific optimizations. Much of it we've covered already, and then also some of it is at the level of determining the kind of CPU affinity that the processes have and the threads have, and existing outside of Python and other optimizations that can happen outside of Python. And OpenVino is another Intel project that supports a similar kind of workflow where they give you a library framework and you run your code through this library framework for having it optimized for a number of Intel-specific compute platforms. And then nn.compression is another GitHub project, a library that does, again, pruning and quantization and all of the stuff I just mentioned, except it, I think, focuses a little bit more on convolutional neural networks. And then Furiosa, Habana, and the others, probably AWS Inferentia, could go on that list too, are just third-party services that you throw your model onto their service and then they do all of the labor of making it efficient. One nice benefit of using PyTorch, especially in versions beyond 1.12, is that there's now a system called Better Transformer, which is essentially is a reworking without changing the API of the various transformer prefixed words that I have listed here. They use, again, all of the techniques I've covered, but within each of these different classes within PyTorch to improve the speed and efficiency of the models that are based on transformer architecture. So for me in the NLP world, this is extremely useful. I didn't have to do anything. I just had to upgrade my, my version of PyTorch, which might be prohibitive. It is very interesting, the magnitude of power that just switching to the higher version of PyTorch to get Better Transformer can have on your model. So we have here a chart that shows baselines for how much padding your tensors have and the latency for inference for processing that. And after you switch to Better Transformer, we can see that the gains that we have as padding goes up are not incalculable, but significant enough to warrant making the jump and doing any of the labors necessary to move PyTorch versions. And then finally, we have another tracing option, which is called Onyx, and calling it a tracing option is a little bit of a, is selling it a little short. It's a very extensive system, but the primary use case is to pull your model again out of Python and put it onto a system that has closer relationship with the hardware, the compute hardware that your model will be running on. So the process involves first putting your model through Onyx, feeding it some test data that looks a lot like the data that you'll be using during inference time, and specifying a few important fields for whether or not, for the various optimizations that you would like it to do. And then once you have traced and exported your model, which again will have the same limitation as I mentioned earlier, no branching logic or nothing hidden behind branching logic will be traced, unfortunately. But after you have traced and exported your model, you can take that to any other runtime, just like the TorchScript traced model, where if you perhaps have your inference, all of your other boilerplate inference code in C++, you can then run your model in C++ or Java or wherever else. In this case, Onyx has also a Python library that allows you to stay within Python for whatever reason, and run your model through there, through the library, through Onyx, and with the expectation that this library, the Onyx library for the Onyx runtime, has optimizations built in for your CPU, in this case CPU, that you would not have exposed in typical Python.
Marcelle, 1 minute, please.
Say again?
Oh, 1 minute, but it looks like you're at references.
Yep, I'm all done. Essentially, this is all the stuff that I just talked about. These are links to them. They're super easy. They don't take as much time as they used to. And you probably need to be doing it, especially since you can't afford a language model as large as ChatGPT.
Excellent.
Do we have any questions?
We'll have to take those outside.
Okay.
Thank you, guys.